In this video, we are going to talk about pH and the pH scale, including pH and pOH calculations. Before we can get to that though, we must talk about the three different types of acids. We have monoprotic acids, diprotic acids, and triprotic acids. A monoprotic acid, as the name mono meaning one and protic meaning proton, indicates, a monoprotic acid has only one ionizable proton which it can donate. An example of that would be HCl. It contains only one proton that it can donate, therefore it's a monoprotic acid. Diprotic acids have two ionizable protons, meaning it has two hydrogens that it can give away. An example of that would be H2SO4. Lastly, triprotic acids have three ionizable protons. An example of this would be H3PO4. This would be a multiple choice question on the exam. Now let's talk about the pH scale. Recall from junior high that pH stands for potential of hydrogen, and the pH scale ranges from 0 to 14. Remember that from 0 to 7, we're looking at acidic compounds, and from 7 to 14, we're looking at basic compounds, and at 7, we're looking at neutral compounds, like water. Know some examples of acidic compounds and know some examples of basic compounds as they come from our household. You're sure to see that in the future. As well, a general rule of thumb is if something has a pH of 0 to 2, it's considered a strong acid, and if it has a pH of 12 to 14, it is considered a strong base. The pH scale is a log-based scale. And you'll notice that we're going to be looking at logs when we look at the calculations. For the purposes of Chemistry 3202, this is all you need to know about the pH scale with its relationship to the log scale. And we'll talk about the log scale in a lot more depth when we get to the IB material. For each decrease of 1 pH unit, the acidity of a solution increases by a factor of 10. Again, I repeat. For each decrease of 1 pH unit, the acidity of a solution increases by a factor of 10. This is a common mistake on assessments. Again, a decrease of 1 pH unit increases the acidity. The reason for that, again, if we were to look at the pH scale, as you decrease down the pH scale and get closer to 0, the acidity increases. Okay, that's a little bit backwards in terms of the way we usually think. For each decrease in 1 pH unit, the acidity of a solution increases by a factor of 10. That means if we decrease by, say, 2 units in the pH scale, the acidity of the solution will increase by a factor of 100. If we want to make a general formula for this, we can write that the acidity is equal to 10 to the pH change. Put in a capital H there. For instance, if we have an example and the pH changes from, let's say, 6 to 3, then we can very quickly find the change in the concentration of H3O positive. That would be equal to 10 to the, well, how many pH changes do we have? We had 3, so it would change by 1,000. Make sure you know this as it pops up a lot as a multiple choice question. Let us now calculate pH using the equation given. pH is equal to negative log of the hydronium ion concentration. Note, for Chemistry 3202, this formula is given on your data table. To practice using this equation, let's go through several examples. First, let's calculate the pH if the hydronium ion concentration is 1.0 times 10 to the negative 7. So in this question, the hydronium ion concentration has just been given to us. So we can plug that into the formula, negative log 1.0 times 10 to the negative 7. If this was a Chemistry 3202 question, you can simply plug this in on your calculator. However, remember, for the multiple choice portion of your IB exam, you are not permitted to use a calculator. So please notice the relationship when we have a base of 1. And for the IB exam, you would only be asked this question when the base is 1. As well, there is a different set of rules for significant figures as it relates to the pH scale. This is written out for you on the worksheet. However, you might want to write this down now so you can remember it for the remainder of the lesson. In significant figures, when you're asked to calculate the pH, you will give the answer so that the number of decimal places equals the number of significant figures in the concentration. For instance, look at the concentration 1.0 times 10 to the negative 7 and ask yourself, how many significant figures does this have? And you should see that this has 2 significant figures. Therefore, when you give a pH, I will be looking for 2 decimal places, meaning 2 numbers that come after the decimal place. So again, the rule is, when you're giving an answer for pH, it must have the same number of decimal places as there are significant figures in the concentration. Let's backtrack again and let's discuss what the answer would be when we have the base of 1. And when we have the base of 1, the pH will always be equal to the positive exponent. For instance, here we have the exponent negative 7, so our pH is going to be 7. Since we have to have 2 numbers after the decimal place and it's just 7, we're going to put zeros there as placeholders. So the answer is 7.00. Now let's calculate the pH if the hydronium ion concentration is 1.0 times 10 to the negative 5, very similar to the last example. So we have negative log of 1.0 times 10 to the negative 5. To practice for the IB exam, let's try to do this without a calculator. First, look at the concentration and ask yourself, how many significant figures does it have? And in this case, it has 2 significant figures. Therefore, I'm going to be looking for a pH that has 2 decimal places. Since the base is also 1, let's look at the exponent. It's negative 5. Therefore, the answer is going to be the positive version, 5. Since I need to have 2 numbers after the decimal place, I'm going to put zeros there as placeholders. Let us now try an example when the base is not 1. Since the base is not 1, this would not be a multiple choice question on the IB exam. However, it's game for paper 2. The question says, calculate the pH when the hydronium ion concentration is 6.99 times 10 to the negative 11. So we have negative log of 6.99 times 10 to the negative 11. The first thing you need to ask yourself is, how many significant figures does the concentration have? 6.99 has 3 significant figures. Therefore, I'm going to be looking for a pH with 3 decimal places. If you are working along with me, you may want to input this on your calculator to ensure you can use it appropriately. Negative log of 6.99 times 10 to the negative 11. This will give us an answer of 10.156 to the appropriate number of significant figures. Let us now try several examples where the hydronium ion concentration has not been directly given to us. Calculate the pH of a solution of 0.497 molar nitric acid. The first question you need to ask yourself is nitric acid a strong acid or a weak acid? You can look at your acids and bases strengths table if this was Chemistry 3202, but ensure you have this memorized for the IB exam. Nitric acid is in fact a strong acid. Recall that strong acids ionize out 100% to their products. So we will have HNO3, and that ionizes out into H positive and NO3 negative. Also recall from the modified Arrhenius theory that H positive and H3O positive can be used interchangeably. So even though the equation is negative log of H3O positive, it could also be written as negative log of H positive. We've been also told that nitric acid has a concentration of 0.497 molar. Also notice that the relationship between the nitric acid and the hydronium or H positive ion is 1:1. So it also has a concentration of 0.497 molar. So pH is equal to negative log, in this case, of H positive. So it's going to be negative log of 0.497. Again, ask yourself, how many significant figures does the concentration have? And you should see that it has 3 significant figures. Therefore, your answer should have 3 decimal places, and that would be 0.304. This should make sense. We have identified nitric acid as being a strong acid, and at the beginning of this video, I identified that for the most part, strong acids will have the pH of 0 to 2. 0.304 falls within the range of 0 to 2, so we have confirmed that nitric acid is a strong acid. Now let's try to calculate the pH of a 1.3 times 10 to the negative 2 molar hydrobromic acid solution. Ask yourself, is hydrobromic acid a strong acid? It is. So we can take HBr and know that it ionizes 100% into H positive and Br minus. We were told that hydrobromic acid has a concentration of 1.3 times 10 to the negative 2 molar. And notice that there is a 1-to-1 relationship between hydrobromic acid and the H positive proton. Therefore, it also has a concentration of 1.3 times 10 to the negative 2. Therefore, we can calculate the pH by using negative log of the H positive ion, or negative log of 1.3 times 10 to the negative 2. Ask yourself, how many significant figures does this concentration have? And you should see that it has 2 significant figures. So you can plug this in on your calculator and make sure you give the pH to 2 decimal places. And when you do, you get 1.87. Again, having a concentration of a strong acid of 1.3 times 10 to the negative 2 has the pH fall between 0 and 2. Let us now work in reverse. Let's calculate the hydronium ion from the pH. So let's flip it. What if we're given the pH and we've been asked for the hydronium ion concentration? Well, if pH is equal to negative log of H3O positive, then H3O positive will be equal to the antilog of negative pH. We just simply do the reverse. Notice that the antilog button on your calculator can also be represented by 10 to the. Therefore, we can write H3O positive as 10 to the negative pH. Again, make sure you know how to use your calculator. Let's work with this by going through several examples. A vinegar sample with a pH of 2.89. Let's calculate the hydronium ion concentration. So the hydronium ion concentration is equal to 10 to the negative pH. Notice that we're doing the opposite of what we were doing on the last page. Therefore, the rules of significant figures are the opposite. Since we're calculating the concentration, our answer is going to have the same number of significant figures as there are decimal places in the given pH. In the given pH, we've been told that it is 2.89. So ask yourself, how many decimal places does this have? And you should see that it has 2 decimal places. Therefore, we should give a concentration with 2 significant figures. So we're calculating 10 to the negative 2.89. Therefore, we're going to have an answer of 1.3 times 10 to the 3 moles per liter. So notice here we're calculating concentration, and we know that concentration does have units of moles per liter. What is the hydronium ion concentration of a sample of blood with pH 7.4? So again, we're looking for the hydronium ion concentration given the pH. So it's 10 to the negative 7.4. Ask yourself, how many decimal places does this have? It has 1 decimal place. Therefore, our concentration should only have 1 significant figure. And it is 4 times 10 to the negative 8 moles per liter. Now let's look at pOH. As the name suggests, in comparison to pH, pOH refers to how basic a solution would be. The pOH scale is also based on the logarithmic scale, and the formulas associated with pOH are very similar to that for pH. For instance, and you don't need to worry right now in chemistry about this log base 10 thing. For instance, when we were calculating pH, let me write it up here, it was equal to negative log of hydronium. And by now you should associate hydronium with something being acidic, and you should associate hydroxide with something being basic. So if pH was equal to negative log of the hydronium ion concentration, then pOH is going to be equal to negative log of hydroxide. As well, when we were finding the hydronium ion concentration, we used 10 to the negative pH because, again, hydronium and acid should go together. For hydroxide, it's now equal to 10 to the negative pOH. So you can see how these formulas look very similar. The final formula in this section is that if you take the pH, or how acidic something is, and the pOH, how basic something is, that will always equal 14. Let's do some practice with this on the next page. Calculate the pOH for each solution. And let's first look at a 0.7 molar potassium hydroxide solution. You should identify potassium hydroxide immediately as being both a strong base and an ionic compound, meaning potassium hydroxide is going to break apart into its component ions, K positive and OH minus. We have been told that the concentration of potassium hydroxide is 0.5700 molar. Since there is a 1-to-1 relationship between potassium hydroxide and just hydroxide, it is also going to have the same concentration. Therefore, we can calculate pOH by using negative log of OH minus, which is negative log of 0.700. Recall in this section that we're looking for pOH, which is very similar to pH, and the rules for significant figures are the same. The answer you give for pOH should have the same number of decimal places as there are significant figures in the concentration. The concentration has 3 significant figures, so we should have 3 decimal places. So the answer would be 0.155. This should make sense. We're talking about pOH here, and we've identified this as being a strong base. So this should be at the very lower end of the pOH scale. If it's at the lower end of the pOH scale, then it would be at the higher end of the pH scale, which is exactly where we know bases are. Let's look at lithium hydroxide. You should also see that lithium hydroxide is both an ionic compound and a strong base. It's a strong base because it contains the hydroxide ion. Therefore, it's going to dissociate out 100% into its ions. We were told that lithium hydroxide has a concentration of 0.0300 molar. Since lithium hydroxide and hydroxide have a 1-to-1 relationship, the concentration of hydroxide is also 0.0300 molar. So we can find POH by using negative log of OH minus, which is negative log of 0.0300. Ask yourself, how many significant figures does this concentration have? And keep in mind that you don't count significant figures until you reach the first non-zero digit. Therefore, 0.0300 has 3 significant figures. Therefore, POH should have 3 decimal places. And this would be 1.523. Let's put this all together now. For example, a properly calibrated pH meter shows a reading of 9.88 for a cleaning solution at 25 degrees Celsius. Calculate the POH, the hydronium ion concentration, and the hydroxide ion concentration. So in this question, we've been told that the pH is 9.88. We can very quickly calculate POH because remember that both of them add to give 14. So I can say that POH is equal to 14 minus the pH. That would be 14 minus 9.88. So we'll very quickly either do that in your head or on your calculator, and you would get 4.12. I can also find H3O positive by using the formula 10 to the negative pH. So there's 5 formulas introduced in this topic. Write out those 5 formulas on a scrap sheet of paper or something and kind of get into the motion of remembering what these are. Then it's easier to know which one to use for each question. So I have 10 to the negative, the pH is 9.88, keeping in mind our rules for significant figures. So 10 to the negative 9.88. 9.88, remember we're now calculating concentrations. We're going to have the same number of significant figures as there are decimal places in my pH. My pH has 2 decimal places, so I should have 2 significant figures. And that would be 1.3 times 10 to the negative 10. And then don't forget to include your units since you're calculating a concentration. OH minus concentration is 10 to the negative POH. You could also use the KW expression from the last lesson. Either would be perfectly acceptable. And this is equal to 10 to the negative, let's get the pen going here, 10 to the negative 4.12. Notice that this POH also has 2 decimal places. So we should have 2 significant figures, and that would be 7.6 times 10 to the negative 5 molar. Let's try one last example. A window cleaning solution has a hydroxide ion concentration of 7.9 times 10 to the negative 4 molar. Calculate the pH of the solution. If you have written out the 5 equations that we've been introduced to in this topic, or if you're just familiar with them at this point, you should realize that there's no one equation that links pH to the hydroxide ion concentration. You should also know that there are multiple paths that you can take to get to a final answer. You could use the KW expression to find the hydronium ion concentration and from that find pH. Or you can take the hydroxide ion concentration and find the POH and from there find the pH. Either path you choose is perfectly acceptable. I'm going to find POH by using negative log of OH minus, which is negative log of 7.9 times 10 to the negative 4. Negative log of 7.9 times 10 to the negative 4 with its 2 significant figures will give me a pH of 3.10. From there, I can then find pH by subtracting the POH from 14. So it's 14 minus 3.10. Also notice that I've been placing the same number of decimal places in 14 as I have decimal places in my pH or POH. And this will give me an answer of 10.90. At this point, you're fully equipped to answer the remaining worksheet questions.